Good morning, cadets. Yesterday we discussed about the electrical energy and the power, electrical energy dissipation and the power dissipation. If you remember, electrical energy dissipated through a device of resistance R when voltage V and current I are maintained, then it is you can say Vi delta T, right? Therefore, from this we got the power dissipated as P equal to energy dissipated per unit time, energy per unit time. So, if you write it as delta W by delta T, so this you can take it as delta W. This is what we have taken yesterday as delta W, right? This is the work done in driving the charges to maintain a current I through a time delta T when a potential difference V is applied across the conductor of resistance R. Now, rate of doing work is, that's how we define it as power dissipated, that is energy dissipated per unit time. So, that is what we get Vi delta T by delta T cancels. So, we got power as energy dissipated per unit time, using Ohm's law. If V is potential difference, if V is the potential difference across a device of resistance R, if V is the potential difference across a device of resistance R, then using Ohm's law, what does it say? Using Ohm's law, V is equal to Ri. So, when you substitute in this equation, then power dissipated P becomes equal to V Ri into I. So, that becomes I square R. So, this is what we term it as ohmic loss. The ohmic loss is due to the resistance of the conductor or resistance of the device. So, the ohmic loss is also called as power loss in the form of heat or Joule's heating effect. To give you example for power dissipation, when the filament of the bulb is heated to incandescence, see, tungsten filament, when tungsten filament of the bulb, when we pass the electric current through the tungsten bulb or filament bulb, what happens? The tungsten filament of the bulb is heated to incandescence. Tungsten filament of the bulb is heated to incandescence. I told you what is incandescence. Heating a material to very high temperature, more than its red hotness. First, when you heat it, the metal becomes red hot, then it will become blue hot, then it will become yellow hot, then finally it becomes white hot. So, when it is heated to incandescence, the filament of the tungsten filament is heated to incandescence. It dissipates the power in the form of heat and light. That is what we call it as power dissipation. and the tungsten filament of the bulb is heated to incandescence, it dissipates power in the form of heat and light. So, this is one example. If you take a heater or electric iron, power dissipation is in the form of heat, right? In the case of a filament bulb, it is power dissipated in the form of heat and light when the filament is heated to incandescence. That is why that bulb is called as incandescent bulb. Bulb is called as incandescent bulb, whereas tube lights are called as fluorescent tubes. They are called as fluorescent tubes. You must know all this. You must have studied this in lower classes. What are the hot sources of light and cool sources of light, cold sources of light? Tungsten filament bulb is an incandescent bulb, which is a hot source of light, and fluorescent tube, LEDs, these are all cold source of light, right? So, that is different aspect. So, power dissipated is in the form of heat and light. Okay. Now, this is the required power, which is useful power, right? Then, when this is the power that is dissipated in the form of heat and light, then from where does this bulb get the power? That is the question. From where does the bulb get the power? Yes, the bulb gets the power from the source. In the case of classroom or in your home, we get the power from alternating current, mains, we call it as AC mains supply. So, basically we get alternating current from the current generating stations, AC power stations, right. So, that is for large scale supply and large scale transmission, we depend on alternating currents, which we are going to study in the last topic of this, last but one topic of this physics part 1 in class 12th, right. Whereas, in particular in this topic we are learning mainly DC sources, what we use in our laboratory, what we use in our wristwatch, what are the sources that we use in our wristwatch, what are the sources that we use in our mobile, right. They are called as cells. You know, cells are the sources of voltages or sources of power. So, this bulb should be connected to a source of voltage or source of power. The simple source of power or voltage is the cell. The cell consists of two electrodes, one positive electrode, right, and one negative electrode, and these are immersed into a electrolyte. These are immersed into an electrolyte. So, this is just symbolic representation. This is electrolyte, electrolytic cell, that is why it is called as electrolytic cell, and this is the bulb which is to be glown of resistance R, see symbolically I am just showing it. This is a bulb of some resistance R is connected to this positive terminal of the positive electrode of the cell, and then the negative electrode is connected to the other end. So, when the circuit is closed, then what happens? A potential difference of V is applied, a potential difference of V is applied across the ends of this, bulb, across the ends of the bulb by this source, so that it allows a current I, to flow from positive terminal to the negative terminal. So, this is how the current flows from positive terminal to the negative terminal and the circuit is closed. So, when the current flows, what happens? Immediately you will find glowing of the bulb. So, here the power dissipated is given by V into I, power dissipated in the bulb. Yes, power dissipated, I need not write it again and again, this is already written, power dissipated through the bulb, that is P equal to Vi, but power dissipated in the form of heat can be understood with I square R loss. I square R loss is called as ohmic loss or the Joule's heating effect, loss due to Joule's heating effect. Okay. Now, this is for the small scale. What about the power that we receive for our locality, for our village, for our entire city, right? We are receiving the power from a long distance, from the power stations, from power generating stations, hydroelectric power station, right? Thermal electric power station, Kudgi, hydroelectric power station, Shakti Nagar, isn't it? So, we get the electric power from a very long distance. Shakti Nagar, I think it is also thermal electric power station. So, similarly, we get hydroelectric power station at Almaty, which is giving you a small scale power, and Bhadravati, Jog Falls, there is a hydroelectric power station which gives required amount of a huge amount and large scale. And then Kaiga atomic power station is there at Kaiga, Uttar Kannada, Karwar. So, there also huge amount of power is generated. So, from all these generators, from all these power stations, we need to get the power. So, power is transmitted through long distance, hundreds of miles from the power stations to our homes and factories. When the power is transmitted through hundreds of miles from power stations to our homes, it is transmitted through the lines, power lines you must have seen, connected from city to city, through the fields, power lines, thick power lines you must have seen. So, it will be written there, high voltage danger, high voltage danger. When you are moving through your fields and all, you must have seen wherever the thick power lines are there with the huge poles, with the huge towers, you see high voltage danger is written. Why that high voltage danger is written? Now we will understand. See, when the cables or lines are drawn from power stations to our locality, to our cities or our villages, it will be of hundreds of kilometers. So, cables of hundreds of kilometers are required. So, then naturally cables of hundreds of kilometers means you can think the resistance of that hundreds of kilometers of line will be very high. Hundreds of resistance will be, resistance of that hundreds of kilometers of lines will be very, very high. Then how to minimize this power loss? Power loss will be always there. How to minimize this power loss? Right? More than the power demand of a particular city, the power loss through the cable will be very high. Then how to minimize this? So, that is the next aspect. How to minimize power loss during transmission? Yes. Power loss during power transmission. Suppose this is a long cable of certain resistance RC. RC to represent the resistance of the cable, and to give you, it may be say several hundreds, right? From Shakti Nagar to or Bijapur city, it may be nearly 300 kilometers. So, you can just imagine what is the resistance of 300 kilometer power line, 300 kilometer metal wire, right? That is resistance of the cable. If RC is the resistance of the cable line, resistance of the cable line, resistance of the cable line connecting power stations with our homes and factories, then let us first write what is the power loss. Power loss through the cable, power loss through line. So, we can call it as line power loss. Line power loss is written as PC. PC, as I have told you, it is I square RC loss. What is I here? Where I is the current that is flowing through this. where I is the current. Suppose this is representing power station. This is power station, and usually it will be two line. It will be two line, and here is symbolically I am just drawing the receiving end of the station, power station to our what you call a grid. It is actually called as grid station. Grid station at a particular locality, at a city. Grid station at a city, you can say. Grid station at a particular city, locality or city. From this grid, the power will be further distributed, right? So this will be of several hundreds of kilometers. Then power loss is very huge. PC is equal to I square RC, where I is the current through the cable. I is the current through line. When I is the current through the line, I is the current through the line, as we have discussed earlier, for potential difference of V. When V is the voltage, when V is the voltage applied across this, is V, then the current that is passing through this one is I. Then we know that power demand for that locality is P. Then if P is equal to IV, we know that P is the power demand. P is the power demand of the homes, power demands of the homes and the factories, power demands of the city. Then we know that P is equal to VI. This is what we have already discussed. P is the power, that is useful power required for all our home purposes, industrial purposes of the to run the factories and all the commercial purposes in the city. So if the total power is written as P, then P is equal to VI. This is the useful power that we need, whereas PC is the power loss through the cable. I think you got it. This is the part of the power that is lost through the cable. Then P is the power demand of the city, P equal to VI. Then this I, this implies I is equal to P by V. When you substitute I equal to P by V, then power loss, line power loss, you can write line power loss. Line power loss PC is therefore equal to, look at this, I square. What is I square? P square by I square RC, that is equal to P square by V square into RC. P square by V square into RC. It means PC is directly proportional to resistance of the cable. Power loss, you see, power loss PC is directly proportional to resistance of the cable. Longer the length of the cable, more the distance of the station from the city, definitely we need longer length of the cable, maybe of several hundreds of kilometers. So this RC is resistance of the cable, right? Second one is PC is very important thing. PC is inversely proportional to square of the voltage, where voltage is the voltage that is maintained between the power station and the city locality, that is V. So PC is inversely proportional to V square. This is very important thing. The RC can be minimized to certain extent by taking the cable of thicker and thicker cross sectional area. You know, resistance is inversely proportional to cross sectional area, means by taking the line or cable of thicker and thicker cross sectional area, by taking thick wires, thick lines, the resistance can be reduced. That's why you must have seen the lines which are drawn through your fields, long distance lines through high tower pillars. You know, you must have seen high tower pillars, must have seen the thick wires are drawn. So it is because thicker the wires, larger is the cross section area, less is the resistance. This is one option. Second option is transmit the power at high voltage. If you transmit the power at high voltage, then what happens? Power loss through the cable is reduced. So this is how we discuss. Power loss is, that is ohmic loss. Ohmic loss through the cable is inversely proportional to square of the voltage. Square of the voltage. Inversely proportional to voltage. So you have got the option here. By using transformers, you can step up the voltage to a very high voltage, 40,000, 80,000 voltage, right? So by increasing voltage, you can reduce the current. By increasing power, P is fixed. P is fixed. So if you increase voltage, what happens? Current I is reduced. The product VI is constant. So if you increase voltage, current I is reduced. So when the current I is reduced, you can see when the I is reduced, definitely power loss through the cable is reduced. So that is the advantage of transmitting the power at high voltage power. Transmitting the power using high voltage rate, high voltage rating. Therefore, power loss during the power transmission can be minimized by high voltage transmission. So power loss can be minimized by high voltage transmission, right? So you must have seen away from the cities, when you go out, you must have seen the boards written, danger boards written in red color, high voltage danger, high voltage power line. It means the power that is transmitted through those lines will be of the order of 40,000, 80,000 volts, right? So this is the advantage of transmitting the power at high voltage, so that current is reduced and power is minimized, the power loss is minimized. This power demand will not be affected. Power loss during transmission will be minimized. So when you are transmitting from the power station to the particular city or locality for the home appliances and for their factories, you have to account for this power loss. And accordingly, the power should be generated at the power station. Okay. These things we are going to discuss in detail later in the topic alternating currents. Okay. Now we shall go ahead with the combination of resistors. There are two types of combination of resistors: series combination of resistors and parallel combination of resistors. Already you have learned these things in class 10th. So just you can say, when the resistors are connected in series, what happens? The total equivalent resistance of the combination R becomes equal to sum of the resistances of the individual resistances, individual resistors. R is equal to R1 plus R2, right. So, when two resistors, let us say R1 and R2 are connected in series, so end to end connection, for example, the left terminal of R1 is connected to the right terminal of R2 and the left terminal of R2 is left free and the right terminal of R1 is left free. When these free ends are connected to the battery, such a combination is called series combination. When R1 and R2 are connected in series with a source of voltage, source of a battery, then current I is the current that flows from positive terminal of the battery through the resistors, and that's how circuit is completed. So, when they are in series, the thing to be noted here is that the current that is passing through R1 and R2 is same. Whatever the number of charges that are pumped from here, what is the functioning of a battery? Battery is to pump the charges, that is to drive the charges. Whatever the charges that are driven per second from the battery, same charges are entering from into R1 and the same charges are leaving R1 and again same charges are entering R2 and leaving R2. So, number of charges entering per second and leaving per second through R1 and R2 is same. Therefore, current I remains same. When the current I is same through R1 and R2, then total potential difference across R1 and R2, if it is V, then V becomes equal to potential difference across R1, that is V1, plus potential difference across R2, that is V2. V is equal to V1 plus V2. So, what is V1 here? According to Ohm's law, I R1, because I is the common current, I R1 plus I R2. Voltage is divided. When they are connected in series, voltage is divided as V1 plus V2. So, if you take out I common, then it becomes I into R1 plus R2. So, V by I is equal to R1 plus R2. So, that implies R1 plus R2 is equal to R, where V by I, if you take it as total voltage divided by total combination of the resistors in series, if you take it as V by R, then current I is same, therefore, V by I is equal to R. So, R is the resistance of the combination of these resistors. Therefore, R is equal to R1 plus R2. If there are n number of such resistors connected in series, same current flows through all the resistors. When same current flows through all the resistors, then total equivalent resistance of the series combination, total equivalent resistance of the series combination is equal to sum of the resistances of the individual resistors. This is the equation for series combination. Now, let us see parallel combination. Okay, let us now see the parallel combination of same two resistors. See here, this is R1 and this is R2. Then both the left terminals of R1 and R2 are connected to a common terminal A, and both the right terminals of R1 and R2 are connected to another terminal. Let us say this is A and this is B, right. When these are connected to a source of voltage which supplies a voltage V, then such a combination is called as parallel combination, right. So, what happens when it is connected in parallel? This is positive terminal and negative terminal. The current I starts flowing from positive terminal of the battery and it enters through the end A, and after entering into A, you see it finds two branches. So, the total number of charges that are entering per second, now they are divided into two paths. The path which is of more hurdle will be carried by less number of charges per second, and the path which is of less hurdle will be carried by more number of charges per second. That is quite natural. So, accordingly the currents will be divided as I1 and I2, so that same currents charges they combine here as I2 and I1, so that the current again total current I becomes same. So, here the current is divided as I equal to I1 plus I2, and here is the voltage V. What happens? Voltage V across both the terminals, whatever voltage is there across A and B will be same across R1, will be same across R2. Potential difference will be same. PD across AB, PD across terminals AB is same as PD across R1, PD across R1, that is same as potential difference, that is voltage across R2. So, this is the thing to be remembered. When they are in parallel, potential difference remains constant, it remains same. Then if V is constant, that is I will write it as same potential difference V. Then what is I1? From the diagram, I1 is equal to V by R1 according to Ohm's law. So, V is equal to R1 I1, and here I2 is equal to V by R2. So, if you substitute in this main equation, we get therefore I is equal to V by R1 plus V by R2, where V is the common potential difference. If you take it out common, then it becomes 1 by R1 plus 1 by R2. So, when V is taken out common, take this V to the left hand side. So, it becomes I by V. So, what is I by V? I by V, if you look at it, I by V becomes the reciprocal of total resistance. I by V becomes reciprocal of total resistance. So, I can write it as I by V equal to 1 by R1 plus 1 by R2. So, that is how I by V, when we substitute with 1 by R, we write finally 1 by R is equal to 1 by R1 plus 1 by R2. So, this is the equation for equivalent resistance, when the resistors are connected in parallel. So, reciprocal of the equivalent resistance, when the resistors are in parallel is equal to sum of the reciprocals of the individual resistances. Okay, this is for the case of resistors. It is just reverse of the capacitors what we have studied. Okay, we will elaborate these things and solve problems based on this in the next video. Thank you. Have a nice day. Bye.